All right, let's try to get it started, guys. I'm gonna close the door just so you can move it. All right, guys. So welcome to another meeting of the AI Club. So this is gonna be the last meeting of the semester, yeah, this time it will be more of a general meeting, though we will probably go into some of the more mathematical part of vision transformers. So anyway, so make sure before we get everything started, scan the QR code and make sure you're registered to the event. This will help us with the logistics for our next semester. And also, we're officially not sponsored by Mingly. It's a connection app where you can go into events and meet industry professionals. And my hope is that we can have some of our events be hosted on their app, so we can have industry professionals to come here and hire somebody. That would be cool. But yeah, if you're interested, it's a new startup local to Dallas. You can download the app with this link. But yes. Sorry, may you please scan the QR code to register, please?
Okay. Thank you.
Yeah, no, thank you. So, brief AI news. Has anyone? Hi, Noah.
What's good?
What's going on? Grab some chicken?
I'm chilling. Oh, we got canes.
We got canes this time.
I just got done with 2 finals, and my brain has been cooked for the last 3 hours.
Yeah, I bet. So yeah, some quick round of AI news. So a few things has happened in the model of nothing ever happens. I don't know if you guys enjoy that meme. Anyway, in the biggest news is Google, right? Google came out with their Gemini 3 large language model. So the significance of Gemini 3 are mainly 2 things. First, the fidelity in code generation. I'm currently using anti-gravity. They're basically the Cursor, Google's version of Cursor, and it's actually good. This time I think it's finally good. So programmers can use code gen softwares to write code a lot more efficiently without trying to debug it, spend all the time debugging it. Second, and this is the news that made the NVIDIA and AMD stock fail, is Google allegedly used their TPU to train their Gemini models. So as we know about model training, you need the operations of neural networks, deep neural networks like pre-trained generative transformers, needs GPU. It needs computational power, right? We can't stress that enough remotely. So basically, the significance of using TPU is that it seems to be a computational unit that is specific for deep training and neural networks. And instead of graphical processing unit, GPUs that are more general to not only to just matrix multiplication tasks like image, like neural network inference or training, TPU seems to be excel at neural network training, and Google does not sell those TPUs, right? That's computational power and computational advantage specifically just to Google, right? Specific to Alpha. And but today we're not talking about that, right? I mean, Google have their image generation tools like Nano Banana. It's a funny name, by the way. And then OpenAI came up with Sora 2. And of course, we always have stable diffusion, the kind of the OG of image generation, right? But we've moved on from stable diffusion to vision transformers, in the sense that we have vision transformers that not only understand text and can generate text, they can generate image as well. Right? So if you go on ChatGPT and ask it to, hey, generate me an image of blah, 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 it'll generate it for you. Right? So basically how we viewed image has changed. So let me go back in time a little bit. There is a professor at Stanford University called Li Feifei. What Dr. Li did is that she gathered a big corpus of database of just images, right? Just images of various kinds, stock images, some other images she bought. She web scraped from Google. I think I may be wrong, but I think Google tried to sue her once because she trained her model on like all of Google's image, so she like scraped all of that. But what she built out is a entire data set of image, and in one of the competitions of image recognition, she blew everybody else out of the water with, I think, something like a 90% accuracy in terms of identification of certain objects. So that's I think 2014, maybe 2013, that's when image recognition just became plausible in deep learning and AI space. So at that time, we were using CNNs, convolutional neural networks, right? So last time we introduced transformers. We talked about how attention mechanism works within the transformer architecture, by processing data into query key value matrices. We're able to calculate the inter-token representation and relationships between each token in a sequence of text. However, what CNN does is taking the entire corpus of your data, ingest it part by part, and then try to reduce that to a smaller size of embedding in order to reduce that to our classification model. So what convolutional neural networks, for example, ResNet, are built on inductive biases. So we will assume that pixels correlate strongly with neighbors, right? Which makes sense. If you have an image of a cat, you probably see like the entire face of the cat, and what's next to the face, maybe the neck, maybe the body. So there's always a pattern there, right? So it will correlate the pixels, and then by convoluting each part of the image, it will process the images hierarchically. So let's say, and that's also called the sliding window mechanism. You're sliding that window of image from let's say this whole slide is the entire image. I will begin with like the upper left part, and then process each blocks of images all the way down to the entire image, right? However, how vision transformers difference from that is that the bias, instead of are for the locally invariance for the patterns capturing, it tends to favor the permutation invariant set processing. So we treat images, instead of like relations regarding to each other to correlate neighbors, we treat them as sequences, right? So think about LLMs will treat text like a sequence. LLMs also treat images like a sequence of tokens. So if an LLM sees an image of a cat, it will try to turn the image of the cat into tokens, just like how it turns text into tokens by tokenizing each text and turn them into embedding space. So yeah, so then that means the benefit of vision transformers is that your every patch the attention for every patch is global. Every patch attends to every other patch, and that's what CNNs don't have. CNNs, at best, relate to the previous and the next convolutional windows, and vision transformers completely kind of abandons that and then make sure every single image token attends to all other image tokens. So, what is the vision transformer architecture? Right. Vision transformer architecture basically builds on top of the transformer encoder that is in LLMs, and it will, yeah, like I said, patch the tokens image into tokens. So each patch will be a individual token, and it will flatten it, and then do the linear projection into the encoder space, and then it will do the classification of, hey, what is this image, right? So for this image, it may be something like a silhouette of a sun, and then that will take the image transformer will take in the linear projection into the encoder, and MLP head will do the classification relating to the text of these image, and that's how vision transformers are trained. And that's just the encoder. That's what we got into yesterday. Last meeting with multi-head attention mechanism in the transformer architecture. So basically, how we model embeddings in patches is that we have for each entry we have class, and then we have each patch into the encoder, right? And then positional embedding just marks which token it is. Positional embedding is also very necessary add-on to text encoding as well. And then we flatten it because we're trying to treat an image as a sequence, right? So we will turn this image and then turn it into basically a 2D image as a stream, a list of 1D image. So we're trying to take this into a list of embeddings instead of like convolutional neural networks. I would relate to each individual ones, but then maybe on a bigger scale as well. So it's more capturing the local, the local features of the image. Now, this is the multi-head self-attention mechanism we've discussed last time, the softmax of QK transform V over D of K, the dimension size. So there's nothing really new there. Just think about images, that image tokens are the same as text tokens. But this time, there's something we need to do to correlate those images to our text. So then, of course, the CNN was good, but to a point it was not efficient because of the bottleneck in its complexity. So ResNets is a classic convolutional neural networks that we use to classify images, and they are very data hungry, and it finds itself hard to converge based on the based on some of the feature space that we go into, and it's very hard to train at first. However, one day OpenAI just lets everybody know, hey, guess what? GPT now can classify, can recognize dogs, cats, and cookies now, or whatever image you may feed it. So how did ChatGPT resolve this problem that was essential to ResNet and the early vision transformer? What they did is they used two separate streams of data, two modalities, text and image. So they take text and image. So for example, let's say we have a dog, and then we tell the text, hey, this is a dog, right? So, and then it will be fed into both encoders. So now all of a sudden we create a vector of what this image is, and we have another vector of what this image is, right? So so then this image encoder will turn each individual image to one of those embeddings. So let's say this dog is right here, and then this image is I1, and then the text is the T1, right? So when you calculate the attention between the two, well, not attention, sorry. If we calculate the distance between the two, whether we do dot product distance or cosine similarity or Euclidean or Manhattan distance, we're essentially trying to correlate the embedding space of this single image and the embedding space of our text, right? So what we want is that if we have an image of a puppy and we have text saying puppy, we want those two to have a similar distance so that next time the transformer see the image of a puppy, it will say, oh, that's a puppy, right? Because that's where in the embedding space, the embeddings are close, right? So what this learning paradigm is called the contrastive learning. So basically, we're maximizing the similarity of the correct image and text pairs, and we're pushing away the distance between every other pair. So if there's an image that's dog, and then the other texts are, let's say, cat, I will want to push away the distance between dog image and cat text, and pull close the image of the dog with the text of dog, right? And that is encoded in our contrastive learning loss. That is our learning paradigm for our neural network. So yeah, basically we have a raw features from the image and the text, and then the joint embedding space will be expressed in the sense of, well, this is linear projection in L2, so Euclidean distance normalized. This is actually just pure distance on a space. So Manhattan distance is like, let's say in the city of Manhattan, right? You have two buildings, you need to walk through the blocks to get there. And then Euclidean distance is just drawing the straight line. I know, how shocking, but it's literally Pythagorean's theorem that we've learned in third grade. But in multi-dimensional size, you just, instead of do the 2D with 3D Pythagorean's theorem, you do it over all of the dimensions. So that's where we get our distances between the features and the weights. And now we can do something called info NCE loss. This is a kind of loss that is used, a cross-entropy loss that we use for contrastive learning, where we can do a pre-training side, and then we can do a data classifier side of so pre-training and the inference side of ML pipeline. So for the loss, what this is basically if we have exponent of IT over the tau, which is the amount of dimensions that we have, so we normalize it. Right here we're doing dot product similarity, which doesn't matter, but basically we count we will take the embedding space of every other pairs and push those away, and for the ones that are close, that are similar, that we count that as a positive pair, and we bring that one close. Right, so after the entire training paradigm, after we go through the n by n matrices of data that we train on, we should have a aligned latent space where the text text embedding will relate to the image embedding. So when the model sees the image of the dog embedded into the image token, it will find the closest text token, which also should be dog in this case. Right, so, but we see how the amount of data that we're training on is actually quadratic to the actual amount of data that we have. So we have positive pairs, but then for negative pairs, we have all the others, right? So now all of a sudden, the model has a lot to learn. It of course learns what is what, but it also learns what is not what, right? The image of the dog is not the text cat or car or school or buildings. Right? So then, during inference, we can take the same text encoder and image encoder, and then find the closest space within your image embedding and then your text embedding to see, oh, this image is a photo of a dog, because I've trained it so that this image latent space would be closest to this specific text embedding, which is dog. And then it will classify and tell me this is an image of a dog, right? We trained it with this paradigm. When we inference, we'll get the same paradigm. All right. And for our zero shot, it's basically this is a Bayesian probability classifier, right? So given what we have in our in our data point, so let's say, should I use this one actually? Yeah. So like given our image that is, let's say this Rolex clock, and then feeding into the vision encoder, we can find the similarity across all the labels with our text encoder, and then we will find the exact match with the highest probability being the one that we pre-train on to say, oh, this is closer to, let's say, Rolex watch. So why do we want to use CLIP to train visual transformers, right? Why don't we try to just use CNNs or ResNet? So I think it comes down to these three, right? So vision transformers trains really fast because it avoids convolutional operations that is in convolutional neural networks. So convolutional neural networks process of convoluting the entire image, kind of reprocess every single patch is really inefficient at a large scale. When vision transformers just treat it as an entire sequence, calculate the softmax at self-attention score, and it's done. Right? And then for scaling, there's CLIP's data set doesn't requires a backbone that doesn't saturate, basically meaning that your vision transformers won't really overfit to a certain data set. Let's say if you use convolutional neural network, it will capture the very detailed local, features and image patterns. But let's say if it train on everything that is every cat as an orange cat, the next time it sees a white cat, it may not think that it's a white cat. It may think it's a dog because it's not seen a white cat before. But it's easier for vision transformers to generalize because it not only tells you what things are, it also tells you what things are not. So you will, even if our data is purely trained on white cats, we will also tell it it's not a dog. So next time it sees an image of a different color cat, it won't predict, hey, this is a dog. It will probably say, well, not seen this before. But it may still be like closer to the image latent space of a cat rather than some other stuff. And also, convolutional neural network doesn't use softmax attention while multimodal neurons in vision transformers do, right? So then it may capture the better abstract concepts. For example, Spider-Man, right? Like what's Spider-Man really in to language model, right? If you think about Spider-Man, you're probably thinking about an image, and that's fine. But if we train a model to relate Spider-Man, the text, into just an image, you may have a hard time to really transpire into, oh, maybe Spider-Man also means like something else, right? If Spider-Man isn't played by Tobey Maguire, is it still Spider-Man? Of course. I mean, we have so many birthday, costume Spider-Mans doing ridiculous things on TikTok or YouTube, right? But we will still call that Spider-Man. But the benefit of vision transformer is that we already have a large language model that does this part really well, right? Encoding the text. And then the benefit of having that, having this abstraction is that we can relate the image to the text as well. So we're just basically, given what LLMs already know, train it on something a little bit newer, right? So CLIP's mathematical alignment of the latent space. Latent space basically just means embedding of text and image. Is the foundation to any stable diffusion models, the current vision transformer models. I think that's it for contrastive learning. That's the best ones we've gotten so far. So what stable diffusion model is like in terms of difference to vision for transformer models is that instead of training a QKV matrix, it will train a noise sampling algorithm where you will sample the noise and you're trying to denoise that image. So that's what stable diffusion is in a very short description, right? But the problem with stable diffusion is that it's just a little bit too big to really converge compared to vision transformers, and the latent space correlation may not be as strong as just an encoder that does QKV. And of course, you can do semantic search outside of generation because this is basically what it's trained on. It's really just semantic search and classification. So what we can do next, if we have the energy to, is we can get into the mathematicals of CLIP, of vision transformers. I have a workbook that I gotten from this Substack site called AI by Hand. It kind of runs you through the entire. It kind of runs you through the entire process of how you would do. This sounds fun. I think Noah's hooked.
Go for it.
This is good because
You're the one that's gonna be doing the math, not me.
I am doing the math, okay? I will do the math. Okay, the benefit of doing these kind of exercises kind of really, outside of me just like saying it, it kind of tells you, okay, what exactly is my algorithm on my GPU actually doing, right? So especially for computer science students, I think this is really essential. So let's say, for example, what we're processing here are basically words and embeddings, right? So let's say for my words, I will have, for every batch of images. So of course, when we're training a machine learning model, we will have we need to have data points of text and image pairs, right? We have a pair of, so we have, let's say we have a batch of 3. Right? Maybe 400 millions more because that's how many image pairs original CLIP models are trained on. And of course, they were a little bit bigger than those. Then what is this, like 8 pixels? And they're colored, so instead of just black and white. But let's dumb it down, right? So we just basically treat every single dark. Oh God. Wrong one. We'll treat every single dark pixel as 1, and then we'll treat every single white as 0. And just as a very basic baseline of how things may look like. So for my, wait, I thought this is my color. That's curious. Is this the right color? Yeah, there we go. All right, so okay, so let's say for this pair of data, right? So for big table, right? Do we see the table? This looks like a table. This looks like a little chair. That's why he did it like this. So let's say for this pair of data, right? So we have big table. So I would, how would I embed the text and my image? So for the text is a lookup table, right? So for the text big, I will retrieve the vector of big, which is 101. Let's assume that's what it is, right? I mean, in real world, it will be a lot longer of a sequence, and each embedding will mean something, kind of. It's not really, but kind of. That's how LLMs embed data, essentially. And then we will have table to be another embedding, right? So it's just a lookup table for now. And then we will turn we will turn this into the first word embedding space. So then we'll have like 1, 0, 1, and then 0, 1, 1. And then for the next one, we have mini chair. So mini will be 0, 1, 0. And then chair will be 1, 1, 0. And then for the next one, we have top hat. The hat, right? So top hat, I will look up top, which is 1, 0, 0. And then hat will be 0, 0, 1. All right, right now we've just finished the encoding, text encoding, right? So we have two encoders. See, the left side is the text encoding. The right side, the green ones, are the image encodings. So let's say we will now encode the images. So let's say I will basically take, again, we will take patches, right? So let's say we treat this half as the first patch, and then this half as the second patch. So then I will bring those over here, and then that's my encoding, image encoding of this big table image, right? Of this 4x2 little image. It's an image regardless, right? You can kind of make out of it that it is a table. So I just flatten it, so that's gonna be 1, 1, 0, 1, 1, 0, 1, right? So 1, 1, 1, 0, and then 1, 1, 0, 1. It's basically how I'm modeling the image embedding as well. So this is all 0 right here. I'm getting lazy, so I'm just gonna only write the ones. And then 1, 1, 1, and then 1, 1, 1. This is the top hat. Yeah, essentially. All right, so now we finished encoding, right? Let's we finished embedding. So we're just finished tokenizing, and after tokenizing, we go into encoding, right? So what encoding does is basically projecting this into a space that is shared, into an embedding space that is shared. The reason why we care about this shared embedding space is that only if we have this shared embedding space does my image and text comparable, and we can calculate the image of both, right? If I'm just doing the distance of this and this, I mean, first of all, the dimension doesn't match naturally, and second, this doesn't mean anything yet. The image is literally just the pixels, right? So I don't want that. I want to use addition mechanism to capture some of the underlying patterns in my image, and then the underlying syntactic and semantic features of my text as well. So let's focus on text for so far. And of course, usually it wouldn't look like, well, what this is right here, the red is a weight vector. And usually it wouldn't be just a weight vector, right? Usually it will be QKV, but we will simplify the math a little bit. So we will get -2, 1, 1, sorry, did I write -2? That's 2. So 101 times 101 plus 0. That's basically matrix multiplication. And then plus the bias. That's how I got 2, right? So 101 times 101 plus 0, 1 dot product. I know 101, that doesn't make sense. But yeah, you're basically taking the dot product between these two vectors and then plus the bias. So that's the math. And then -2 over here because it's 0, 3, 0, 1, 0, 1, which is 0, and then -2. We won't deal with minuses for now, just for simplicity's sake. We'll just cross that out and then treat it separately. Maybe treat it as 0 for this case. So then the next one, 1, 0, 1 plus 0, and then 1, 1, 1, that's 1. This is 3 minus 2, so 1. 1 over here, that's gonna be, and then that's gonna be 2. I click something. I swear one day I will get an iPad. I have an iPad, it's just 10 years old, which is not good, right? And then this is also gonna be 1. 0, and then 0, 0, 0, and then 1. Okay. So now we have our basic text I still need to mean pool and then round it, round because I don't want to deal with. I want to deal with integers today. So let's just take the mean of my text encoder. So you see how we kind of converted this embedding space into some other space, but then we're also just taking the mean of all of those and then like kind of concatenating down. So I don't know. I mean, to some extent, the knowledge representation of vision transformers, transformers in general, is still like very similar to CNNs, but it's just in the sense that we're not really doing the relations between each of these. We're kind of just taking them into a simple sequence, and then later on doing a better projection in order to train it with vision tokens. So then we multiply this by the projection matrix, and projection basically brings these two vectors down to the shared embedding space, right? Projection is the last step that we need. So let's say projection will be 1, 1, 0, 2, -1, 0. Right. So now this is the text embedding. This is the final actual embedding of my text. And let's find image on the image side. It will be the same math, of course. This is what your GPU is doing, by the way. But you realize how in your GPU, this process and this process is like simultaneous because you have multi-threading where it's just calculate these 4 times. But if you're doing it in your CPU, then it has to calculate everything one by one. Versus for GPUs, your multi-threading will enable it to reduce the complexity from cubic to quadric. That's why we do GPUs for all of the transformer training. It's because of the complexity of matrix multiplication, right? So if I go down this, 1, and then over here is 2, 3, 0, 1, 0, 1, 1. I won't deal with negatives for my mean pool. 1, 3. Do we actually? I think we actually clamped this though. Maybe in the original clip. So we won't have anything beyond, like below 0. Anyway. 1, 2.
Where's that 2 coming from? The first, that row, the second 2, the one under it. Yeah, how do you get 2 there?
So 0, 1, 0, 1 multiplies a dot product with 1, 1, 1, 0. 1, 0. The first 0 multiplies with 1. That's 0. The first 1 multiplies 1. That's 1. 0 multiplies by 0. That's still 0. So 1 multiplies by 0, 0. So 0 plus 1 plus 0 plus 0.
Got it. 0,
That's 1. And then I add the bias.
And then you add that one. Oh, okay.
Yeah. And then, right, so then we add this bias. So the bias term is basically after the matrix multiplication, we add on this bias to make it a 2.
Okay, and the 3?
The 3 will be this row times this column, right? So
plus
0.
1.
Yeah. So
Okay.
so right, this row times this column will be 2, and then we plus 1, that will give me 3. Right. That's just matrix multiplication.
That's what a GPU is doing.
Yes.
But like I imagine on a much bigger scale.
Yes, on a way bigger way bigger encoder, like with maybe instead of this is 4x4, maybe like 512 by 124, something way larger, right? And if your GPU has like I don't know, like a few million cores, then all of a sudden 1,000 by 1,000 matrix doesn't sound demanding at all.
Okay. And the top use cases for this sort of math is really just language models in like video games right now? Or like is there anything else?
Yeah, so matrix multiplication is only applied when you treat things like a matrix, right? So what a matrix is just a 2x2 list or a 2x2 array. So image is a classic example, right? So let's say I want to, if I want to display a movie, that's like image. So every frame will be like 3 megabytes of freaking data, right? That's a lot of data, but that's not where the processing comes in. That's just the display. But if you want to play video game, what's going on is that you're treating each object inside of your video game as a vector.
Yeah.
Now, every time you move that model, have you seen like those like graphics testing softwares where it's like there's a little horse that's like spinning and it tells you like the FPS?
No, I haven't.
No. Have you seen like 3D animation softwares
Yeah.
where it's like you build a model, whatever it may be.
I've seen like this is like Minecraft, like Roblox. Or
Okay,
something.
let's say Minecraft,
Yeah.
right? So let's say you're a Minecraft character, just Steve standing there, right? But let's say I want to change my field of view. I'm Steve, and I'm looking at Steve in third person, and I want to change my field of view. So everything in the world, including Steve, are represented as vectors, right? So like so basically lists of data that marks each point of Steve where Steve is. So the moment I turn Steve around, I need to change that vector in this 3D space to see and then project it down to 2D. Every time you move your mouse on a video game, your GPU is doing that.
Yeah.
It's taking every single vector in the entire field of view, let's say there's a Steve right here, of every single vector inside your Steve, every single vector inside of each block. It's taking those, turning it to whatever degree alongside with your mouse, and then projecting back to 2D. And that requires matrix multiplication. So you basically takes all of those vectors, multiplies by the degree that you've turned your camera, right? And then you will get a new vector, and then you project that to 2D. But that needs to happen. Let's say if your game runs at 60 frames per second, that needs to happen, right? Within like 12 milliseconds.
Yeah.
And that's a very fast operation, considering how many vectors that we have,
Yeah.
right? And for games that run like 300 frames per second, you can imagine how fast the GPU is processing that every frame, right? That's why NVIDIA is like pushing DLSS, because basically what DLSS, do you know what DLSS is? It's frame generation. So basically, when you're playing games, sometimes when nothing too much is happening, when like your character isn't moving too much, you have the capability of kind of just predicting what the next frame is gonna look like.
Mm-hmm.
Though you may look weird, but it will basically kind of give you it will lose less frames, because then it will save time for the GPU to calculate the real frames,
Mm-hmm.
right? So these are some of the hacks that GPU manufacturers have been using to kind of give gamers a better FPS to convince gamers to buy their card. But yeah, so games, right? And 3D animation is basically the same thing, but like they have more detailed textures. So it's basically the same thing. And then and TPU would do that. Besides, it's just not geared towards graphics. So I mean, maybe TPUs can run graphics. We just don't know. They never really show it to the public, show their card to the public. But let's say GPUs are specifically geared towards, I want to change my entire image or entire vertices into an image, right? But why is it also good at this? Well, because while processing images and then like playing games is matrix multiplication, training a neural network model is also matrix multiplication, right? These are all the matrix multiplication that's happening, and every time we calculate we calculate it with matrix multiplication, we'll get a loss function, and based on that loss function and the gradient descent, of its derivatives, we will update these weights and then calculate it again. And then we will take the loss, take its derivative, and then calculate the weights, adjust the weights, and calculate it again. So what machine learning really is we're calculating these vectors again, and again. And every time we calculate that, we just change these weights just by a tiny bit until after I don't know how many million times that I train it, this will resemble something that will capture something in my data that will generalize for a more generalized tool. So let's say for text generation, or in this case for image and text latent space convergence and text classification. Does that make sense?
Yeah.
And for inference, we just kind of run it once, but it will still take time to even just run this once, right? Depending on how big your model is. Yeah. So in the age of we have like, I don't know, 100 billion parameter large language models, having a big VRAM is important so that you can fit this and all of these operations inside of your GPU, right? So if we do mean pooling again, this just takes the mean of like everything between here and here. So let's say, 2, 2, 1, 2, 1, 1, and then 1, 3, 1, 2. Let's say I don't take the, and then you pull it down to projection, so you calculate this, minus 2, 3, 2, 2, that's gonna be 2, and then 0 again, 1, 0, and then 2, 1. Later on, yeah, okay, so now we are finally at the shared embedding space. So we finally finished the run through the encoders, and then we have embedded our text and image data. Now we are going to calculate the softmax of the softmax attention, right? So basically, your scaling your numbers in let's say in this case probably like -1 to like 3 space to the certain range. So it's with activation, so it's better easier for your models to calculate the to like kind of capture the close range numeric relations. So let's say in the softmax of this. And softmax, right? So e to the power of whatever, e basically almost equals to 3. So that's kind of a good way to think about the value of softmax. So for this, probably the same here because it's e, and then, well, let me copy this down for now. And then when I try to relate it back to, okay, I'll copy the embedding first, actually. 2, 0. Let's say that's I1, image 1, right? And then 1, 0, and then 2, 1. So now I just need to calculate and then do softmax. So again, first I do matrix multiplication. That gives me 2, 0, -2, 1, 0, -1, 2. So 2 times and plus 1, so 3, 2, -2. And then we take the softmax. So basically, we're trying to multiply, not multiply by 3, but 3 to the power of this. So let's say 3 squared is 9. 3 to the 0th power is 1. Negative, we'll just turn this into 0. So we can just clamp it. These are 3 negatives. And then will be 3, 1, and then 27 and 9. I'm not a math guru. I kind of don't really get the softmax and QK type of relations, because I know there's some ways you can kind of represent the number in ways that you can kind of represent that without calculate the whole softmax to improve your complexity. But at the same time, yeah, this is just sum. I haven't got into that space of research yet. It seems quite arbitrary for actual real world use, but I know it's something that's, you know, essential in like efficient machine learning training. 39, this is 11, and then 0. Okay, so then we can calculate two kinds of similarities here, and that's another nuance with CLIP contrastive learning, is that you can calculate the similarity between text to image. You can also calculate the similarity between image to text based on how you reduce, like by which order do you calculate your matrix and then divide by its sum. So basically you kind of, after all of this, you get two similarity scores as well, right? So let's say for this one, this is like around 0.2. This is like around, let's say 0.1. We can't divide by 0, so just 0. And this will be around 0.1, 0.7, 0.8. And then we calculate it on this side. And then we change it to gear towards the image to text, right? So then we have image divided by like kind of the sum on the text side. So so then it's just another different order. Minus 0.9, 0.1, 0.75, 0.25. This is where my trackpad lacks its versatility. 0.7. Ouch. That's big. 0.3 and then 0. Right? But our target is that these two embeddings should be the same thing, right? They should be both like, not both top hat, but basically both these streams of data. So big table, miniature, top hat, right? So these batches of text should be the same as these batches of images. At least that's the ideal in terms of my loss. So basically, I will compare it with the target, which is 1, 1, 1. So remember, we have the positive pairs here. Positive pair, positive pair, positive pair. So these should be 1 and the rest should be 0. And that's my target that we're trying at. So the benefit of this is that now I can calculate binary cross entropy. Well, not binary actually, because I have a lot more data. So I can calculate cross entropy, and the cross entropy formula is the y hat minus y. So my target y minus the actual y that I got from my calculation, and then divide by the amount. So for the loss, then if we take the loss gradients, if you take the chain rule, then your loss is literally just this minus this. So again, right, you suddenly realize a lot of these tricks that we use here really isn't geared towards like mathematically this makes more sense. It's geared towards computationally this is simple, right? Because I just need to calculate this minus this and I get the loss. And then I will use this to adjust my weight up there. So this will be something like negative minus 1. Let's see, 1, 0 is fine because, right, we got 0 over there, so that's perfect. 0.75. Bruh. One day I'll get it. Not in this economy, though. Like 0 and then 0.7, 0.3, and negative 1. Because this is supposed to be 1, not 0, but that's 0, so that's a lot of loss. So then text to image is the same thing, right? Like on the text to image scale, it should also relate to it when it's the same pair. 0.1, negative 0.90. And now I finally have my loss gradients across my across the subtraction, across back into the shared embeddings, and of course it goes into the trainable weights, which is projection, and then the text encoder. So then after I've gotten my loss function, and this is really not the loss, but the how much loss I need to change. I apply this by the learning rate, and then I will back propagate through all of that, right, in order to adjust my weights. So that's clip with its step by step how you would how would a GPU calculate it, and how you would get to the loss, and then adjust your weights, so that you will get to this target range that every single same pair image will correlate to the same pair text. So that's a brief overview of clip. Thank you. Yeah, what time is it? It's like, oh God, I've gone over time. Anyway. Yeah, I'm actually doing something kind of similar in my own research. I'm like trying to do, not with image though, so I'm trying to like correlate two different latent spaces, so this is definitely something that's super helpful for me.